All right. Hello, everybody, and thanks for coming. I'm Will, work at a company called Optimism. You may or may not have heard of us. More likely, you've heard of Optimistic Rollup or the Optimistic Virtual Machine that we're associated with as well. And luckily enough, or kind of unlucky due to the pandemic that's going on, but it's pretty awesome that more or less everybody from my team is also here. So it's great to see them and everybody else who's not in Chicago that decided to join. So yeah, today, as was kind of outlined in the invitation, we're going to go over layer 2 in general at a high level, and then talk through optimistic rollup a little bit, and then the OVM and like the differentiator within optimism for the optimistic rollup, and then kind of the current state of optimism. What have we done already? What are we currently doing? What are we planning on doing in the future? And then a quick little demo of some of the stuff that we talked about today. And like Paul said, feel free to interrupt at any point if any questions or comments you have are relevant to the slide in question or the idea in question. If it can wait till the end, that's better. But if it pertains to the slide, then yeah, let's talk about it then. Cool. So let's get into it. We have about an hour, maybe a little less than an hour, and we're going to work a demo in here as well. So we're probably not going to get like into really deep dive stuff or like a bunch of really complex theory or anything like that. So if people have questions about that and want to hang around after and talk through it, happy to do that. All right, so first things first, why layer 2, right? Before we're talking about like what it is and what it, our approach to it and everything, like what's the idea behind it? One of the main motivators, obviously everybody knows, is throughput, right? On mainnet, we have lower tens of transactions per second, whereas if we can make it so that thousands of computers around the world aren't doing the exact same thing in order to progress the state, then we can do a lot more. Same thing with speed. If that's the case as well, if it's not so massively distributed, then we can accomplish one unit of execution a lot quicker, right? And then, as was mentioned earlier, fees are a large motivator as well. You don't want to be going broke and be having slow execution. And then user experience as well. It's something that doesn't really get mentioned as much when it comes to layer 2, but it's really important as well. If we're talking about better throughput and better speed and potentially lower or as close to zero fees as possible, the user experience has a good potential to be much better than layer 1 as well. So what is layer 2? Oh, and you might recognize these slides if you saw Carl's presentation at ETHCC. I've taken a lot of them and used them directly or repurposed them for this talk here. So yeah, like what is layer 2, right? It's basically a state machine. You have your collective state that's agreed upon, and then there's some transition that occurs, and that moves your state along to the next thing. And then another transition moves your state along to the next valid state, right? And so the most current state is called the head state here. And the way layer 2 works is, we want to get this better throughput and this better speed and these lower fees in layer 2, but we are also, the reason it's called layer 2 is because there is a layer 1, and that is Ethereum, and we want to fully inherit all of the security that Ethereum has to offer, right? So every now and again, we're going to take this state and we're going to make it as small as possible, and we're going to submit it to layer 1 so as to get some of those benefits in the form of a state commitment. So then users can look at the head state and see that it's on layer 1 and see that, get that security guarantee as well. So I suppose it's important to mention layer 2 is often talked about in the abstract, but there's potential for many different types of layer 2s or many different implementations of even the same layer 2 solution. So you might be tracking a lot of different, depending on what you're doing, you might actually be paying attention to many different head states at once. And then, yeah, this is all composable, right? So there could be also, I suppose, layer 3 and layer 4 and all the way down. But the whole idea is that layer one, as we talked about before, as many of you have experienced, has limited compute and memory, and layer two, a lot less limited, right? We can do a lot more, a lot faster, and leverage some of the guarantees of layer one, right? And then yeah, as we keep going down, like in theory, yeah, maybe there's even less limited compute. I think Carl in his talk talked about, you know, layer one, the way that we talk about it now is you know, Ethereum, and then layer two would be, you know, any of the layer two protocols, like for instance, optimistic rollup or plasma, or state channels or anything like that. But in the future, layer one could be like the beacon chain, and layer two could be shards, and then layer three might be rollup, right? So really quick comparison of layer two chains, and more importantly than comparison of the chains in question is more so like the mechanisms and the reasons behind them. So, you know, as we talked about before, one of the things that's really important for layer two chains is availability. Like everybody in the world should be able to see what the head state is, right? What is the current state of my stuff in layer two, right? And so like, there are some differences between optimistic rollup and plasma and state channels as to how that availability works. And then there's also validity, right? We need to guarantee, since we're not dealing with the unanimous consensus of layer one on every single transaction, we need to figure out like, how are we going to guarantee the validity? How are we going to leverage that layer one security to you know, secure our layer two chain? So when it comes to rollup, our availability mechanism is pretty easy, pretty simple. We're taking all of the different transactions that occur on layer two, and we are rolling them up, a la rollup, and then we are posting it to the layer one chain, right? So the way that we make sure that our head state is available, and the way that we make sure that all of the transactions that occurred that led to our head state are available, is by posting them on layer one. And then everybody can see from Ethereum that the state, and see that, you know, what the state of their wallet is. Now, validity mechanism is, we're going to post that state on occasion to layer one, as we said, and we have fraud proofs. So if we look at that state, and like we said, all the different transactions that went into that state are also present. So we are able to do, you know, our validity checks ourselves. We're able to run all those from the previous state, run all of the different transitions, see if we end up with the same resulting state. Now, if we don't, we're able to submit a challenge to the layer one chain and say, hey, like, we started here, we applied these transactions, we didn't get the same thing. So something's wrong here, right? So we're able to submit a challenge, and then, you know, prune the invalid state from layer one, right? And I suppose we can go over a few of the differences here for the, you know, other approaches, right? So ZK rollup, similar to optimistic rollup, except that the, you know, validity mechanism is, you know, a succinct ZK proof, right? So that whole challenge thing is not required for ZK rollup. And then plasma, it's the same, you know, kind of the opposite, the same validity mechanism for plasma, except for the availability mechanism is slightly different, right? Instead of submitting all the transactions to the chain, it's incumbent on you to keep track of all the transactions that are associated with the state that you care about. So it's much harder than optimistic rollup. And then state channels, yeah, unanimous consent for everything. And, you know, there's a bounded participant set. So state channels are a little bit different than everything else. They're really appealing, but also not really like, you know, globally useful for everybody and able to use as a single protocol for everybody. Cool. So let's move forward. All right, so walkthrough, and this might get into the weeds a little bit. I'll try to like, you know, breeze through it, but if you have any questions along the way, please, you know, let me know. So starting the chain, right? As we said before, like we fully inherit the security from layer one, and the way that we do that is by posting our contracts on layer one, and basically we are defining the rules by which we're going to play in layer two on layer one, and that defines all the you know, challenges and validity proofs and everything like that. So we define our optimistic rollup chain by deploying our contracts there. Sweet, we have a chain. Now we also have aggregators who are going to be the ones who are actually advancing this layer 2 state and posting these commitments onto layer 1. And what is important is for them to post a bond so that if they misbehave, if we do challenge them, that they have something to lose. There's a disincentive for them to lie or misbehave. And I guess it's important to point out that there can be many different aggregators. At any given time, there will only be one, but they are redundant. For right now, we're just going to assume that there's one. So entering the chain, how do you do that? So if I want to enter the chain, I'm going to send a transaction to the layer 1 deposit contract and say, hey, I have this money. I want to use this money to join this layer 2 protocol and abide by its rules, right? So then that goes through, it gets mined on chain, and all of a sudden my ETH turns into optimistic ETH, right? So great. Now sending transactions. So remember, yeah, transactions are not going to occur on chain. They're going to be processed by the aggregator, and then they will eventually make their way on chain in the form of their state, but not processed on chain, right? So say I want to send 1.5 ETH to Bob, send it to the aggregator does the processing, deducts 1.5 ETH from me, adds it to Bob, comes up with the state that represents that, and keeps track of all these different states of the layer 2 chain that is advancing, rolls those up, submits them to the chain, they get mined, and that's how the state advances. So submitting a block, right? We have this rollup.sol contract. Submitting a block is just if we view all of the state of all of the layer 2 environment as leaves in a Merkle tree, then we just create a Merkle root from that, and that is our block. That is our rollup block. So we have 32 bytes per rollup block of state, right? So that is part of the appeal here. We can do many different transactions that represent a lot of different state transitions, and the state representation on chain is just 32 bytes. So lots of gas saving as well. So let's see. When the state ultimately gets posted on chain, like we said, we can see that, and everybody can observe it, right? So now interacting with smart contracts. Smart contracts, after all, are just accounts as well. So you can represent this as an account. As long as the aggregator knows the logic of the smart contract, we're able to represent its state as simply like another account. So how transactions work is you send a transaction to the aggregator saying that you want to invoke a specific function of a contract, and the aggregator takes care of it because it knows the contract logic, it knows how that should work, and same sort of thing. Instead of updating an externally owned account, you're updating the contract, right? Create the root, submit it to the chain, and again, everybody can see the updated state. So now let's say that the aggregator wants to act maliciously, right? So I say I want to send 1 ETH to Bob, and the aggregator said, well, it'd be really nice if instead of Bob getting that, if I got that 1 ETH, right? So they include that, and they create a rollup block, and they submit that root to the chain, right? So now, just like all the other ones, that root is on chain, but now we see it, and we're able to say, okay, we have all of the data that went into this, and we know the previous state. We're able to apply these transitions and see that, like, I said that, my signed transaction said to send 1 ETH to Bob, and instead it went somewhere else because, the root is not the same. And what's important is I can see that, Bob can see that, Infura can see that, Etherscan, anybody running a full node can see that. So instead of me having to watch the chain and make sure that my own transactions are actually, that somebody is protecting them, what's nice is all we need is one honest validator to make sure that our transactions are safe, right? And given enough use, and especially people who are, using layer 2 with a fair amount of value, they are going to run validators. And this should be a safe assumption. And we'll get into it later, but you are rewarded if you prove fraud. So yeah, let's get into that now, actually. So challenging invalid blocks. What goes into that, right? We saw that we have an invalid transition because we know that, like, off chain, we were not able to compute the same state on chain given the same inputs, right? So now we know that it's wrong, but we need to prove to layer 1 that it's wrong, right? So how do we do that? Well, we need to, since there's a lot of different state that has transitioned off chain, and since the only thing the chain actually knows about is the state root, we need to, from just the state root and the data that we have off chain that has been submitted as call data, we need to piece together a proof that we can prove to this contract that is incorrect, right? So we'll need an inclusion proof of the previous, we'll need the previous transition and the state of the previous, the inclusion proof of the state of the previous transition, right? So like when I went to send 1 ETH to Bob, I had 7.5 ETH. And I know that I have that because I can prove it from all the different transactions on chain, and more importantly, from the previous transition root, I have an inclusion proof that I can generate that says I have 7.5 ETH, right? So let's go through verified transaction inclusion. So we have, let's see, yeah, this is the previous state. You're able to create a Merkle root or a Merkle proof that shows that the previous transition exists, is right before the one I'm challenging, and is valid. And then the one that I'm challenging comes right after it. That's something that's easily checkable by the contract. So that's easy to prove. Now storage inclusion. So we have, like I said, these Merkle proofs of the starting state of the invalid transition. So I have to piece together a Merkle proof that says I have 7.5 ETH to start. And this empty slot here exists as well, or does not exist, I should say. And then we actually apply the invalid transition. So in this case, it's fairly easy because, you know, the signature is invalid. They changed, you know, like it's not my signature. I did not sign something saying that it's going to the aggregator. But in practice, if the signature was valid, but instead the root was different, then we would be able to find that out as well, right? We send to the chain the proofs required to, you know, like the inclusion proof of the previous state as well as the transition. The chain itself then actually does the computation, and it sees that it's not valid, right? So now what we had just talked about is that's how it would ultimately check the resulting state root. In this case, we already succeeded because the signature is invalid, but yeah. Now, if the challenge succeeds, right, we remove the block in question, the invalid block. And this is the part that I was talking about where if one honest validator exists, we're safe. This is why there will probably be one honest validator, is because we burn most of the deposit that the aggregator, or I should say much of the deposit that the aggregator has posted, but we reward whoever challenged part of that bond. So you are definitely incentivized to challenge invalid transitions. Cool. So, yep. So yeah, then this aggregator dies, goes away, and as we said, anybody who posts a bond can become an aggregator, right? So they post a bond, somebody else, you know, is selected to fill the void, and they're able to build on that chain with the invalid state removed. Sweet. So I have to thank Carl for this one, but yeah, we just sort of put a blockchain on the blockchain, right? So I think I'll pause here really quick and see like if there's any questions. We kind of went through a fair bit here, but hopefully the idea is pretty simple. We run all the stuff, we actually compute it off chain. The only time we actually run it on chain is when we're proving that somebody misbehaved. And that's where the bulk of our speed up comes. Cool.
One question I've got is something I've been a little bit fuzzy on in the past, and I think you touched on it, but I think it'd be helpful if you expanded on it just a little bit or clarified maybe. So on chain in the actual like layer 1 state, you're posting the Merkle root of the rollup state. Is that accurate?
To like as part of the challenge, you're saying?
As just
or
as any, like,
yeah.
not part of the challenge. It kind of is
So
in the original.
yeah, that is how the rollup chain progresses, right? Is the Merkle root of the state of the L2 chain is posted and kind of appended to.
So what I think I want, what I'm have been fuzzy on is how, like, where, and I think you mentioned it, but I may have forgotten, but where exactly does the kind of the expanded state of the rollup chain exist? Where can Etherscan or whoever find that?
Yeah, that's pretty important, and it wasn't like explicitly mentioned in the slides, but that is added as call data for each one of the block submissions. So the state that is actually stored as state within Ethereum is, the Merkle root. However, we post as call data all of the different transactions that made that state what it is, that transitioned the state from the previous Merkle root. But notably, it is not actually processed by layer 1. So we are still using layer 1 for storage, although not storage the way that we store everything else on the chain. This is call data, which has gotten massively cheap recently. I think it's, 16 gas per byte, if I'm not wrong. So
Okay,
yeah.
cool. That's very helpful. Thank you.
Yep, no problem.
There's also one more quick question in the chat. Marto said, what's the incentive of the aggregators? They get some ETH? Maybe I missed that.
Yeah, so that wasn't explicit either, but yeah, the aggregator will, like we said, that the promise of layer 2 is lower fees, but there still will be fees, and the aggregator will still be rewarded. It's just, due to economies of scale, they can charge much less for each individual unit of work, and still make a decent profit while making stuff cheap for you. Cool. So now getting on to implementation. So the first thing that we wanted to do was, okay, we understand optimistic rollup, and we want to implement a simple proof of concept, get it in users' hands, see if there's a there there, right? So back when we were the Plasma group, we for DevCon last year worked together with Uniswap and created something called unipig.exchange. Many of you might have used it, but in essence, we built out optimistic rollup. We built custom contract code for Uniswap as well in layer 2, and built out all the stuff that we just went through, and except for the deposit and withdrawal, because it's all fake money for unipig.exchange. But we built that out and had a little trading competition at DevCon, and people were able to see what it would be like to use optimistic rollup and see what that user experience would be like. So, this was just a screenshot of a specific trade, but we're looking at less than half a second to get confirmation instead of much longer on layer 1. Cool, great, we're done, right? Or I should say, when are we gonna have more? So all of our stuff is open source, so you can go in and see. As I said, we did create custom contract code, and that makes us sad, because that means that, like, for every single contract that is going to come on layer 2, we're going to need to write new code, and that for a scaling company is not very scalable, right? So we need to be able to do better than that, instead of scaling by writing new contract code for every single thing. So that brings us to the OVM and what we did next. So just to highlight a couple of the problems with layer 2, it's hard to audit, right? If we're one, all of the different layer 2 code needs to be audited, but then if we're writing new contract code that needs to act in complete parity with layer 1, that's really hard to audit, right? Also, every incompatibility with existing developer tooling is terrible, right? Because then you as a developer need to figure out, am I developing for layer 1 or layer 2, and what do I need to change in order to adjust to the environment I'm working with, right? And then like we said, it's a huge burden for existing L1 contracts. If they have to write new code, if they have to maintain 2 different ways of going about things, that's going to be trouble, right? So, like, what we set out to do is we want an EVM that can execute optimistically off-chain, and also execute on-chain, so you can write the code once and use it in both places, right? That would lower your audit risk. That would make your audit spend just one time in order to validate contracts that will work in both layer 1 and layer 2, right? And then ideally, it should be compatible with existing developer tooling and simple to implement and audit, and efficient to evaluate state transitions on chain, right? Like we need it to not take forever or run out of gas, right? So this gets at the motivation, like if instead of Uniswap and custom code, if we could just have a general purpose solution for this, that would be ideal. So that gets us to the OVM. So what our goal with the OVM is if we notice in layer 2 that there's an invalid state transition, that we can run that exact same thing on layer 1, exactly as we said. So the OVM is an EVM implementation, which can be run off chain and then executed on chain. So that's exactly what we're talking about for fraud proofs. And the on-chain OVM evaluation is done inside of a containerized environment. So, before when we said we put a blockchain inside the blockchain, here it's starting to get very, very much more like that, right? So we wrote basically EVM inside of a smart contract. And we'll show you the components of that. But the three are, there's a transpiler. So, there's a transpiler, a safety checker, and an execution manager. So transpilation is the reason that we need to transpile, and the reason, so if we're going to put a blockchain, or if we're going to put an EVM inside of the EVM, and more importantly, if we're going to be able to take layer 2 state transitions and evaluate them on layer 1, we need to account for the fact that they're going to have different states, right? The layer 1 state and layer 2 state are going to be different. There's going to be context that's missing. So basically what we need is all of this to be like a static function that we're able to call in, and we're able to provide it inputs and have the exact same logic and get the outputs that we need, right? So in order to do that, we need to make sure that none of the code that we're using can modify state outside of the state that we're allowing it to modify. So that's where transpilation comes in. So we have the execution manager that we're talking about is literally a smart contract through which all execution flows. So that is our execution context. So anytime that you're going to make a call, anytime that you're going to ask for environment context or anything like that, you're actually going to interact with the execution manager. So that's where transpilation comes in. So let's say that this is your contract code, you're pushing, you're adding, you're storing. Well, the moment you go to do an S-store, right, you are going to modify state that will ultimately affect the context of the layer in which you're working. So we need to transpile that, right? We need to somehow make your contract code static. So what we end up doing is taking that S-store, and instead of you writing storage to the chain, you are instead calling a contract and having that contract deal with it, right? So this is what allows us to, in a static fashion, challenge any fraud proofs, right? Because now we've taken, imagine on layer 1, we're trying to challenge something generically that modifies state. This is how we end up doing it. So we're going to transpile that, and just something to note, like, yeah.
Of the test case from the test setup. I could have multiple extra by individual.
I'm sorry, I didn't hear it. Was that what did you say?
Yeah, there's a little bit of feedback.
Okay. I thought it was a question.
No, I think it was. Sorry,
okay.
I meant that the audio wasn't very clear. If you can try again, or if you want to type that question, I can relay it in a second. But for now, you can probably just go ahead, Will.
Cool. So I guess something to note is that, yeah, so we are, like we said, we're writing an EVM within a smart contract. So that is not going to be as efficient. This virtual environment is not going to be as efficient as the EVM itself. So there's a bit of a gas overhead, but there's zero overhead for state independent opcode. So for instance, if you're adding or multiplying or anything like that, that's not stuff that we need to step in front of, like writing to state or calling an external contract or something like that. So did that question come through, or should I keep going?
I haven't seen it yet.
All right, cool. So the other thing that we need to do there, so our transpiler is what we use to take contracts that you have written for layer 1 and transpile them such that they'll work in layer 2 and layer 1, right? They'll work in the OVM. And so the transpiler will get rid of, or more importantly, like transpile opcodes that are unsafe. And the result of that should be safe, but we still need to implement a safety checker ourselves on chain just to make sure that any contract code that we're going to deploy in the OVM is safe. It doesn't use any of these unsafe opcodes. It instead calls the execution manager to do all of it. So we wrote a safety checker as well. And then there's also our execution manager. So as we said, our execution manager is the static context in which all of this actually takes place. So when you deploy a contract, you call the execution manager with that contract. The execution manager will actually deploy that contract, and it will keep track of the address that you think that contract's at and the address that it knows it is at and its local state, right? That way you can use one address to interact with this contract, whether you're on layer 1 or on layer 2, right? Likewise, if you're talking about timestamp, you don't ask the EVM for timestamp because the timestamp of your transaction that is going on in layer 2 is going to be different than the timestamp in layer 1 when a fraud proof happens, right? So instead, you ask the execution manager for a timestamp. And then what we're able to do, like during a fraud proof, is we actually provide the timestamp. So then when you ask the execution manager, okay, like what is the time of this transaction, instead of asking the EVM and having this mismatch, we're able to make sure that it's the same. Likewise with message sender, right? So, you know, your address, message sender, or really like any of the context that is specific to the chain that you're dealing with, whether it's layer 1 or layer 2. So yeah, like this, when we were talking about S-Store, like this is actually, or hello?
D. Watkins, you're unmuted. I'm not sure if you're trying to talk.
All right, moving on. So we said like S-Store is unsafe because you're going to set storage, and we need to make sure that all of those storage calls are going to go through our execution manager, right? Like when we submit a fraud proof, we don't actually want to change storage on chain, right? We want to execute that storage change through an execution manager that keeps track of, like, you know, how has this state been modified in the course of this fraud that I'm proving, right? So like the SR here, this is the execution manager code. Every time that your smart contract are going to store some value, you're actually going to call the execution manager, and it is going to save your storage on its own associated with your own contract, right? So it keeps track of all of the different state of the entire L2 chain within the execution manager. So that is the same as, you know, all of these different opcodes, right? If you're likewise storing, if you're loading, or if you're creating a new contract or calling another contract, right? If you're calling a contract on layer 1, that is probably going to have a different address than on layer 2. So the execution manager needs to step in the middle of that and do that mapping for you, right? Same with, you know, any variant of call. So yeah,
I have a quick question there, if you don't mind.
Sure.
You feel free to push it, but so with like create and create 2, you somehow presumably have to like also safety check the new thing that's created, right? Like that seems tricky.
Exactly. Yeah. Well, yes, it actually is very tricky. Ben can certainly attest to that if he's still on. He wrote a lot of that, but so that was the reason that there's the 3 different things that we said were the transpiler, which does that transpilation for us, but then the safety checker, and then the execution manager. So the execution manager, anytime that it's actually going to deploy a contract, it needs to know that that contract code is safe, right? And then any contract code that it, you know, will recursively create will also be safe. So yeah, there's a fair amount of complexity there. And so yeah, like the execution manager is basically our layer 2. It is a contract that completely you know, runs the EVM in our context, and then also you know, on chain during fraud proofs. So yeah, there was a lot there. Do we have any other questions before we move on? Cool. Also, I think this was Jing who created this nice little image here. So a little shout out. So current state of optimism.
We got one theoretical question.
All right. I may tap Carl or Ben for this, but let's see.
You actually might have mentioned it really briefly at the very beginning, but could an execution manager, like a separate one, be on the rollup chain, and then have like another rollup that is being executed on the rollup chain?
That's a good question. Theoretically, like, yeah, like we should be able to have, you know, layer 3 and layer 4 and everything. But so our execution manager will be deployed in an untranspiled fashion, right? It will be the only thing that is actually running EVM code, whereas anything else that's deployed will be deployed through our execution manager. So it would be harder for the execution manager to do anything that's native to layer 2. Now that said, yeah, it could run everything through, you know, just like our execution manager leans on the EVM, your layer 3 execution manager could lean on the layer 2 execution manager to then, you know, have it be turtles all the way down.
One other quick question. Do you have any back of the envelope numbers on how much of a storage hog this contract would be if it were being used heavily on layer 1? And also like what the cost would be to keep it running?
Yeah, so the nice part about layer 1 is that it shouldn't have too much storage at all, right? Like we, at the point of fraud proofs, we'll need to make sure that the contracts that are called in the fraud proof transaction in question are actually deployed on layer 1, but they don't necessarily need to prior to that. As well as, you know, all of the layer 1 fraud proof should be static. Like it should not modify state other than potentially reverting some of the state root that was committed as part of that block that is fraudulent, right? So yeah, like the overhead on layer 1 should be very small. Now like we said, we're running the EVM in a virtual environment on layer 1, so each one of these fraud proofs will be fairly beefy, depending on the transaction that takes place. So there might be a large gas fee to prove fraud, but that will definitely be you know, more than compensated for by the reward that you stand to gain.
And is much gas being used for the regular state transitions when you update with the latest Merkle root, or no?
So there, just the 32 byte, you know, state root, as well as like 16 gas per you know, byte of call data. So that depending on how large your rollup blocks are, you know, that kind of dictates the gas there.
Awesome, thanks.
So yeah, current state of optimism is, yeah, as we talked about, we implemented a simple proof of concept with Uniswap. And then, you know, from that, we gain some user feedback, as well as just like the understanding that this doesn't scale well as we want to do. You know, we luckily that was really successful, and a lot of people were like, yes, we want this right now. And it became immediately apparent that we, you know, there's only so many of us, and we didn't want to write more code per contract that gets deployed. So that led right into the creation of our general purpose OVM. And then something that hasn't really been done yet or tested on our side is, you know, this generic L1 to L2 entrance and exit. We wrote some of that code before for Plasma, as well as a little bit for, although it didn't actually get used for the Unipig demo. But there's a couple of different updates that need to be made to it in order to get it to work with our current thing. So there's just a little bit we got to do there. And then eventually we'll launch a public testnet in mainnet. And it sort of goes without saying, but we're planning on validating with users the whole way through. So we kind of validated with users during DevCon last year, and that is kind of what motivated some of the changes in this generic OVM. We are currently, you know, working with a couple of different contracts on layer 1 that need scaling to use the OVM for, you know, to get some of that feedback, to test it in a real environment and get some of that feedback as well. And we're gonna, obviously do that throughout the process. So as part of that, anybody here who is interested in, taking a look around or, kicking the tires on some of this stuff, please go to our GitHub, fork our repo, take your contracts and transpile them and run your unit tests and see if they work. Let us know if there's any bugs. So that is the end of, like the presentation itself. We still have, there's like a short demo I want to show of some contracts that we've transpiled. Also, like I said it before, but I'll say it again, big thanks to Carl. Almost all of these slides are his, so I'm just repurposing them. Before we get to the demo, let me know if there's any questions.
Nothing in the Discord at the moment, but anyone else can feel free to unmute themselves too.
Cool. So let's see. All right, so we can get into demo stuff. Oh, forgot that's here. So you might recall the quadratic funding contracts that Paul and others created for our Chicago Ethereum Meetup, right? There's, let's see, as we get into contract project here, we have, a couple of different, or no, let's go back. We had a couple of different eligible projects that you could vote for, and ultimately, yeah, that would be sort of like Gitcoin in quadratic funding, where like the less that you contribute, the more, or the more individual contributions, the more your contribution would be worth. And so we have a couple of different contracts there. And what I thought would be useful is to take our stuff that we've developed, this OVM stuff and the transpilation, and showing you how, like, what the developer experience might look like, right? So I forked that repository, and we have a couple of different contracts that I wanted to see, like, could we transpile these contracts? Because Paul and them are good developers. There are unit tests, which is great. So what I wanted to see is, like, what is the minimum amount of time that it will take for us to transpile these contracts and see that they work on the OVM, right? So I went into the project, and first thing, I imported our transpiler and our full node that contains the OVM and the, which has the execution manager and the, safety checker and everything. And I had to make a couple of changes to the smart contract, or not to the smart contract. Notably, I did not have to make any changes to the smart contract, but I had to make a couple of changes to the unit tests, mostly just importing dependencies here, as well as the only material change was to swap out the provider that we're using, right? Like, now we're not actually going to use, like a L1 EVM, we're going to use our OVM, right? So swapped out the provider, and what you see as all these other changes is just the fact that our provider, the creation of it, is async. So all this stuff that was done in this base level describe, I pulled it in here after the provider is created. Those are set off of the provider stuff. And then the other material change is just closing our provider at the end of each, or at the end of all tests. And then the same thing for our other set of unit tests, the actual quadratic funding unit tests, right? So our material change is creating the mock provider and then closing the OVM. The other change that I had to make that I didn't really mention because it won't affect many different projects, like anybody using Waffle or Truffle, is that with Builder, they allow you to specify your version of the Sol-C compiler, but for us to transpile, we need you to be able to specify the path to the Sol-C compiler. So our transpiler, the way that it hooks into regular dev tools is by overriding the Sol-C version. We just pass it a path to our transpiler. So as you can see, this is just generic Waffle config, and the only update that you would normally have to make if you're using Waffle is to come in here and, instead of using whatever Sol-C version you're using, use our transpiler. And then, like I said before, make the update to use our provider, and that's that. So then, just to make sure I'm not just smooth talking, let me share this. So now you should be able to see my terminal. I created this OVM branch that, like I said, pulls in our libraries and wires up the tests to actually use our stuff. So when we run the build, this is slightly different than what it would normally do in that it's not using Builder to compile. Instead, this is running through Solc or through Waffle that will then use our transpiler. So it generates the output JSON in the exact same formats and everything. It's fully compatible. And then let's see, we're able to run our tests and see that they all pass. So now what's important here, well, I said see that they all pass before they actually did, but what's important here is, yeah, we're abiding by, Web3 as standard. We're abiding by all the different developer protocols that you normally would, so that you can interact with our layer 2 RPC server the same way that you would interact with any other node. So that really lowers the burden of dealing with, like if I'm developing for layer 1, then I have to use this set of tools. If I'm developing for layer 2, I have to use this set of tools. And I have my debug level a little bit high, so you're seeing some of like the printouts from inside of our node that gets spun up. But yeah, so that's like the only thing that was required, and most importantly, like there's no change to your contracts, no audits that you need to do or anything like that. You just need to come in and swap out the provider and change the compiler. So I think that's it. Any other questions?
Quick question. So I'm not totally sure where is the machine that it's running against? Like, where was the configuration for setting that up?
Yeah. So the configuration for setting that up was just so like, where is the machine that it's running against when you're using Waffle or when you're using Ganache or when you're using Truffle? It's just a built-in local chain that gets spun up.
Oh, okay. Okay.
So that's the exact same thing here. We have our full node that that's part of this create mock provider. That's why it's async, is like it's actually spinning up a node and deploying our execution manager and having that Web3 front end that you hit in order to interact with it. So you, and like the most important part here is that you don't have to change any of your code of your interaction. So your deploy contract, your actual interaction, like your transfer or anything like that, you are speaking the exact same language that you would to an L1 smart contract to interact with our L2 node. And our L2 node is taking that and changing it to communicate with our execution manager. And you are getting the exact same results as seen by your unit test functioning.
Got it. That makes sense. Thanks. And then follow-up question there. What's the testnet story look like for Optimism contracts?
What do you mean by story?
Like if you had a contract that you would have deployed to Ropsten, is there already like the Optimism executor contract on Ropsten and then you just deploy it pointing at that?
No, we'll, so just like, for testnets, we'll need, we'll actually need to run our own aggregators to actually create an L2 chain for our testnets. And we will have a public testnet that's launching in a little bit here. But yeah, like you would then interact with that.
Cool.
And there will be like on Ropsten or on Rinkeby will be the like actual L1 deposit contracts and the fraud-proof contracts and everything like that. Or like the rollup chain contract. We would still be submitting, our rollup blocks to layer 1.
So the mock, is this kind of is this locally launching like Ganache or whatever, like a local L1 and then kind of with your contracts deployed on it?
Exactly. So yeah, like
cool.
Right here when we say create mock provider, spins up Ganache, deploys our execution manager, and yeah, that's
Sweet.
that. Cool. Any other questions, or do you want to get to the casual part of the meetup?
Yeah, I've got one more question. So for that that contract you just transpiled, no changes to the actual contract code itself, which is cool. Are there any instances where there would have to be even slight differences between the L1 version versus the OVM version?
Yes, yeah. So, so there are 3 categories of opcodes, and Ben and Carl can speak to this a little bit better. But one of them is like add, multiply, stuff that is just like static. It doesn't, deal with state at all, and those we don't even transpile. But then there's other ones that do modify state or ask for context, like calls or like timestamp or things like that we need to transpile. So instead of you making this call to an address that may or may not exist on layer 2, instead you tell the execution manager to look for, and they'll look up the proper address and make sure that it's safe and everything. But then, yeah, there is a third category that it should be extremely rare of, opcodes that are fully unsupported. I can't remember the exact ones off the top of my head right now. Ben or Carl, do you remember like which ones are not currently supported?
The big ones that are different are like timestamp, block number. Those are really the big ones. There's like a weird thing with static call, but that's like, neither here nor there. But this is more like a differences probably in the way that they will be implemented. And so that's, a question of, do we want to, give this exact same API and, implicitly there are differences in how they function, or like change the API to like signify that there are those differences. So the feature wise, they should be similar.
Any other questions? If not, I'm going to close this out by switching to speaker view. No, sorry, gallery view. And if everyone can do kind of a virtual round of applause for Will, that'd be cool. So thanks.
Woo!
Okay, thanks, Will.